Welcome to The Explainer. Today, we're going to be architects, but on a scale you can't even see. We're talking about designing the materials of the future, literally one atom at a time. So, what if you could build the perfect material from the atoms up? I mean, really think about that. It sounds like something straight out of sci-fi, right? But this is the question at the very heart of modern material science. Engineers aren't just discovering materials anymore, they're designing them with custom properties for pretty much any application you can dream up. Okay, so to build anything new, you've got to know your tools. And down at this scale, our tools are the atoms themselves and the forces that stick them together. This is where the blueprint for, well, everything begins. It all starts with the bond. Seriously, every single property you can imagine, how hard something is, whether it conducts electricity, how it deals with heat, it all comes back to these tiny fundamental connections. The atomic bond, it's everything. Let's look at two totally different kinds of bonds. You've got covalent bonds and metallic bonds. In a diamond, the atoms are basically locked arm in arm, sharing electrons in these super rigid covalent bonds. That's what makes it so incredibly strong. But in a metal, it's a whole different ballgame. The outer electrons just kind of detach and form this shared sea that flows around the atoms. And that lets the atoms slide past each other. It's why you can bend a piece of metal. And this is pretty much the designer's entire toolkit. You have this whole hierarchy of forces. Up top, you've got those covalent bonds, which are crazy strong. Then way down below, you've got much weaker hydrogen bonds, and even gentler forces called van der Waals forces. By picking and choosing how to arrange these, engineers can cook up a massive range of material properties. All right, so knowing the bonds, that's step one. But step two is figuring out how billions, and I mean billions, of these bonded atoms actually arrange themselves into a bigger structure. And that's where the crystal structure comes in. Just think of it like the material's architectural blueprint. It's this one little pattern that gets copied over and over and over again. And, just like with Legos, the specific way those atoms stack, that has a huge effect on the final product. Okay, but what happens when that blueprint isn't perfect? This is where things get really interesting and, honestly, a little counterintuitive. Because in material science, perfection, it's often a weakness. It's actually the mistakes, the imperfections in that crystal blueprint that give a lot of materials their most useful properties. Yeah, so we've really got to stop thinking of these as defects or flaws. They're more like essential design tools. A missing atom here, a misaligned row there, that's what lets a metal bend instead of shatter. When you apply force, these little imperfections can move through the structure, letting it deform. Without them, metals would just be brittle, useless things. And it's not just about those tiny point defects. The big picture boundaries between different crystal grains, those are also super critical. They act like firewalls, stopping a crack dead in its tracks. So, by controlling the size of these grains, engineers can dial in the perfect balance between a material's strength and its toughness. So, we've got our building blocks, the atoms and their bonds. We've got our blueprints, the crystal structures and their defects. Now comes the really fun part, putting it all together to engineer some truly revolutionary new materials. This is where we get into composite materials. The classic example everyone knows is steel rebar inside concrete, right? Well, the principle is exactly the same for these advanced composites. You take two or more totally different materials and you combine them to create a hybrid that has the best properties of both. The final result is way better than the sum of its parts. Let's zoom in on one really high-performance class, metal matrix composites, or MMCs. What you do here is take a lightweight, bendy metal like aluminum, that's your matrix. It's the glue holding it all together. And then you embed super strong, super stiff ceramic fibers or particles inside it. So what do you get? You get the metal's toughness and the ceramic strength all in one package. But of course, there's always a catch, right? How in the world do you get two completely different materials, a metal and a ceramic, to actually stick together? See, if the bond is too weak, the whole thing just falls apart. But if it's too strong, a crack can just zip right through both of them. The secret is all about carefully designing the interface between them. So how do things stick together anyway? Well, down at the microscopic level, there are a few ways. You can have mechanical interlocking, which is kind of like two rough surfaces just gripping each other. You can have some weaker physical forces at play, or if you want the strongest possible connection, you can actually form direct chemical bonds between the two. Getting this right is absolutely key to making these composites work. And a really important concept for this is something called wetting. For the molten metal to form a good, strong bond, it has to spread out and completely cover those ceramic fibers. Think of it like water on a super clean piece of glass. If the metal just beads up, like water on a freshly waxed car, you're going to get a weak interface, and your composite is going to fail. Okay, let's leave the lab for a minute and head to the factory floor. Let's see how all these principles are actually used to build real-world parts that are pushing the absolute limits of engineering. So one popular way to do this is a process called squeeze casting. You start with a pre-shaped block of the ceramic fibers. You stick it in a mold, and then you inject molten metal under ridiculously high pressure. This intense pressure forces the metal into every nook and cranny, making sure it gets that good wetting we were just talking about. What comes out is a super dense, defect-free part. So you might be asking, why go through all this trouble? Well, the payoff is huge. You get materials that are way stronger and stiffer for their weight. They resist wear and tear and hold up under high-temperature fatigue. You can even design them not to expand or contract with heat, which is absolutely critical for things like precision electronics or anything going into space. And you can see the impact of this stuff all over the place. We're talking high-performance engine pistons that can handle extreme heat because they're reinforced with ceramics. Brake discs that just don't wear out. And of course, super lightweight aircraft parts that save fuel and boost performance. This isn't just theory in a lab. This is technology that's already out there, making things happen. The big challenge, though, is always going to be that balancing act between performance and cost. These custom-designed materials are incredible, no doubt, but their manufacturing is complex, which makes them expensive. So a huge goal for engineers right now is figuring out how to bring those costs down to make these amazing materials more accessible for everyday stuff, like cars and consumer goods. So we're designing materials literally atom by atom. By mastering the architecture of matter, from the bond to the crystal grain, all the way up to the composite structure, we've totally changed the game. The question isn't just, what can we find anymore? Now it's, what can we imagine? What huge problems are we going to solve with materials that we haven't even invented yet?